All right, gang, math 5500. Going to get into leverages, and this video, I guess, is where influences, a lot of things. I don't know where we're really headed, but this this should be the final video of lesson number 7. Okay, so I want to start out first of all looking at leverages, and remember, said earlier that the hat matrix, which we have seen ad nauseum by now, is important in a couple of reasons. First of all, it's very important in being able to project our y's onto our predicted y's, but it also plays an important role in regression diagnostics. Specifically, it's important in IDing x and y outliers. Now, a few properties of the hat matrix. If we just look at the elements on the diagonal, those elements will always be, these H's start to look like a K after a while. I won't use K in any other context in this. So if you see something that looks like a K, it means it's an H. No, 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 I'm wrong. Actually, I do use a K, so I'll just have to write slower, okay? So anyway, these diagonal elements will always be between 0 and 1, in, well, inclusively. The sum of the h sub i's will be equal to, speaking of k's, k plus 1, where k is the number of predictors. So you can think of just k plus 1 as the number of predictors and including the intercept. Now, most importantly for us at this stage, and at this stage we're focusing on leverages, which again, leverages do what? They examine the difference between x and the mean of x. So the h sub i's are an important metrics for measuring the distance from x to x bar. In other words, what we can conclude here is that a large diagonal value from the hat matrix indicates that x is far away. Well, that's the ugliest away I've ever written in my life, but at least I'm speaking it, is far away from the mean of the x's. All right? So the reason of that is because h sub I is actually defined as the leverage of the ith case. So h sub I is defined as the leverage of the ith case. So, plays an important role. Now, what's the metric? Where's the line in the sand? What's too large? Well, in practice, we say that if one of the diagonal elements is greater than or equal to the mean of the diagonal elements, mean of h, then we have a violation of a high leverage, if you will. And you can recall that, and this is why I'm hesitating, I forget. So h is, just going to be the sum of the diagonal elements over the sample size. And this is just going to be, some of the h's is just k plus 1 and over n. So we can clean this up a little bit and say that HII greater than or equal to 2 times k plus 1 over n is a red flag for a high leverage. Indicate again that that particular x, again, your hat matrix is an n by n, right? So every single case, if you have 20 cases, 20 people, 20 subjects in your design, in your study, you will have a diagonal value for each of those cases. If any of those cases, any of those diagonal values is larger than this quantity, then we have an issue. And I'm going to demonstrate this to you a little later. Okay. Now let's move into influence. Again, over the last 3 or 4 videos, I've been consistent. We look at what? Outliers, residuals, right? We look at leverages, and we look at influences. Well, for the influences, what I want to focus on in this class is called Cook's distance. Now, let's pump the brakes a little bit and let me give you indication of where I am, my thought process is. If everyone in Math 5500 also took Math 6500, I wouldn't be covering this section. I would put something what I think is even cooler in here. I would put logistic regression, get into a nonlinear model, just to contrast that model with something that we spent the first 6 lessons on, simple linear regression, multiple regression, right? But because some of you will only take Math 5500, you won't get into a thorough presentation of diagnostics as the people who take 6500. I need to touch on leverages and influences and so on. So anyway, in 6500, I'll get into DF fits and DF betas and variance inflation factors and outliers for Y and some other really, really cool things. But since I want to give you a snapshot here in 5500, I am choosing Cook's distance. Now, what does Cook's distance do? Cook's distance measures the influence of dropping the ith case on all of our predicted values. All right, so we have other measures that we can drop the ith case and it'll give us an indication of how that particular predicted value, that predicted value for that particular case. This even goes further, this being Cook's distance. It goes further to give us an indication or the influence of dropping a particular case on all of our predicted values. Now, the way that we calculate this is we actually, and let me tell you right now, you're not going to use this form to make your calculations, but I think looking at this form actually gives you a pretty good indication of what we're doing here. We'll actually run this from j equal 1 to n, and we'll look at the predicted value for j, and we'll look at the difference of the predicted value for j if the ith case is actually deleted. So that's what that notation means right there. It's the, wait a minute, that should be the predicted value. Yeah, the predicted value of y sub I minus the predicted value of y sub I if this particular case is deleted. Now the standard error here turns out to just be k plus 1 times the mean square error. And it turns out, and again, we have one of these d sub i's for each case. So it turns out that these d sub i's follow an F distribution with degrees of freedom k plus 1 and n minus k minus 1. Now, previously, when we deal with the F distribution, we know that it's not symmetric. And typically what would happen when we jump into a distribution is we, in this case, would find the d sub I, and we would concentrate on this area right here, which we should know by now represents the p-value. All right, pump the brakes. For influences, we don't do that. Our focus on these things is the percent below, or in other words, the percentile. So again, we don't use p-values in this case. We look at the percentile. Now, the metric for using the percentile and making a decision on our Cook's distance, and we can calculate the percentile using just PF and using R, or in that case, any sort of technology. But anyway, if the percentile is less than 0.20, then we say that we have a small influence. So that particular case, any case with the percentile less than 0.20 has small influence. So we don't even consider deleting it because it's an influential case. If we can't write and speak. If we have a percentile between 0.20 inclusively but less than 0.50, then we have moderate influence. And again, a moderate influence, I wouldn't be concerned with. But if we have a percentile that's greater than or equal to 0.50, then I would classify that as a serious influence, and I would then start to take, or at least consider taking remedial measures and most likely deleting the ith case from the study, from the analysis. I ran into this. One of my first doctoral students. I think she was actually my fourth doctoral student, third or fourth. Who's counting? But anyway, she was chair of the occupational therapy department here at Shawnee State University, and she completed her PhD through Southeast Nova University in Florida. So I served on her committee. I didn't chair it, but I was one of her doctoral advisory committee members. And she had the data set. She had 82 subjects, and she was one of the first people to actually collect a data set that looked at some relationships of variables for adults with autism in the workplace. There had been adults with autism, there had been children with autism, but she had the first data set that we could find that really examined these particular characteristics for adults with autism in the workplace. Well, there was one subject number 36, never will forget him, and he was a college professor at a very prestigious university. And all of his observations were just, he was high on the autism scale, but he just didn't have any of this, he didn't score high on some of the other metrics. And we would put him into our analysis, we would include him in our analysis. We wouldn't get statistical significance on some of our models, but if we took him out, we did. So we debated a lot, and we validated running and reporting both models, one with him in, one with him out, based on this kind of stuff. So this kind of stuff. So if I was going to calculate a Cook's distance for a particular person, I would look at the error for that particular person. I would square it. Then I would look at the number of predictors plus 1 multiplied by the mean square error. And then I would dive into my hat matrix, pull out the diagonal element for that particular person. And then I would look at 1 minus, again, that diagonal element squared. So once I get this, and what I want to do, I want to illustrate this for whatever, D3, let's say, with the body fat. I think I predicted body fat from tricep and thigh. So what we would do is we calculate D3. We'll go to our model, whatever this value is, we'll get the percentile ranking, and then according to this standard up here, we'll classify as either small, moderate, or severe, well, or serious. Okay, so we will actually do that. So I tell you what, let's bump out of here. I've already got a lot of stuff already done because I don't want to waste time. But I encourage you to, if you're approaching the class the way I think you should approach the class, you should have R up right now, and go ahead and replicate this stuff. So anyway, this is all pretty clear right here. I just got my data into R, and now I'm going to predict body fat from triceps and thigh. First thing I did is I set up my response vector. Next thing I did is create my ones for my design matrix. All right. Next thing I did is I created my beta matrix, and you can see that my beta estimates are negative 19.2 and so on and so forth. Next thing I did was I create my hat matrix, and then using diagonal, D-I-A-G-H, I can come in and create the values on the diagonal of the hat matrix, and I just call those HII for obvious reasons. So because we have a data set that includes 20 subjects, our hat matrix is going to be 20 by 20. So this is H11, this is H22, this is H33. Sorry, I'll quit. So this would be down to H2020. All right. So I want to look at the range of the HIIs. It looks like the smallest one is 0.05, and the largest one runs to 0.38 through 0.37. Next thing I do is I create my predicted Ys. And again, I can calculate my predicted Ys by just taking the hat matrix times Y.